Hi, my name is Jordan Scott, and my partner is Aiden Farner.
Hello.
This is CST 415. This is Decision Tree and Tree Pruning Project. So here we have our game that we made in Unity, which is we call it Hackathon, just because we have our AI set to be the hacker, and you will be defending off against the AI. So the AI used the decision tree logic to evaluate its moves. As you can see, the game simulation will have different outcomes in real time. This is a dynamic interplay that keeps the game challenging and unpredictable.
So at the core of the AI are the decision tree. So for each possible move the AI can make, the tree simulates the state changes. And this is utilizing a matrix based on Punnett squares, if you remember biology, to predict the outcomes. So each of these has an effect, and each hacker move has an effect. And when they're paired off against each other, one comes out on top, or they cancel each other out. That's the idea of the matrix. The negative values in the Punnett square in the matrix indicate a good move for the hacker, and positive values are good for the um, defender. So as you can see here, starting in state zero, the idea for the game is that the player has to stay in state zero for 5 turns. So they have the least amount of good possible options, which is just zero. Then the middle matrix is balanced, and then the last state is balanced towards the player because they want to win. Um, to make intelligent decisions, we're utilizing a minimax algorithm. It systematically evaluates each branch of the tree and assigns a score based on the current state. When multiple moves have the same good score, the AI randomly selects one to keep its strategy unpredictable. To show off the Minimax AI here, we implemented the tree pruning using alpha beta pruning. As discussed in class, it eliminates branches that won't affect the final decision. In this minimax function, you can see that as the algorithm evaluates each possible move, it updates the two parameters, the alpha and the beta, and prunes branches with the beta value is lower or equal to alpha. Here is the code, as you can see, and it determines based on whose turn it is, and returns the max or min eval. So the alpha and omega, or alpha and
And so
beta.
now we're going to show you. Uh, Now we're going to show you a demo of the game.
Okay, so as you can see here, we're in state zero. Click this button, the hacker goes, oh, I should probably go to console. It goes through all these different moves, it determines the value, and then it chooses the best one, but it got it wrong. The AI does not know what the defender chose until afterwards. But if I hit patch vulnerability, as you can see, the defender was able to move it to state 1. If I hit reset system, it goes back, play honeypot, it moves back, and yeah, this is pretty much it. You can see the state changes and the decisions behind the in the background there. You can see here in Game Manager how many times we've been in the start state, and if it gets to 5, oh, the hacker won. If this got to 5, the defender would have won. But as you can see, I lost, and that's good because we want the defender to have the ability to win.
And so that sums up our project right there. And this is how we use decision trees and tree pruning and how to make a powerful AI that both is efficient and smart with making decisions. Thank you.
Thank you. Have a good one.